we are trying to find the continuous fraction expansion to a given function like this, what you do is to declare x as symbolic variable, and then you have to declare the original function. And since x is already a symbolic variable, you do not have to use the quotations. You can leave them, you can delete them. You can use them as well. So you can specify the original function, and then you can call a maple command cfranc. And finally, what you get is something like this. This is the continuous fraction expansion to the original problem. And you can see that some of the denominators are larger than the previous term, so we can truncate the remaining part of it and simplify the continuous fraction. And finally, you can get a rational function approximation to the original problem. If you write this continuous fraction on and on, you will have infinite terms. If you only need 8 stages to the original function, you can use a function call like this to extract the rational approximation of it. And finally, you will get a rational approximation like this. So maybe there was something wrong. I think these 3 terms are okay. C and E. Sorry, I haven't expressed the original function yet. This is the function. I haven't specified the function earlier. So by the use of these functions, we can easily find the simplified term, the rational function. And this is a rational function. We can display it in a better way. And this is a numerator, denominator, and it is clear that this one is a rational function. So now the question is, if we compare the 2 functions, one is the original function, the other one is the fitting function, what is the fitting result? F is in the interval, I think, 0.00 to 2. Problems. Oh, sorry, FUN. Hold on. And then we still use G is a plot for G. And you can see that these 2 curves are quite close over this interval, 0 to 1.5, something like that. It should be very close. However, if we increase the interval, the fitting result may not be quite good. So by using this kind of rational approximations, you must be very careful with the fitting result and see whether it is close to the original problem. And this one can be compared by using, you can draw the 2 curves together, because in this case f must be a given function, so you can draw them together. If they are far away, then you have to increase the number of terms you have to reserve. For instance, you can increase the numbers here, then you can have a better approximation to the result. And now let's talk something about Paddy approximation. Actually, in literature, we may find that continuous fractions are equivalent to Paddy approximations in certain ways. In continuous fraction, normally we will have the degree of polynomials of the numerator polynomials and denominator polynomials, something like this. So the denominator, the degree of denominator is 1 only higher than the degree of numerator. So continuous fraction. And if in Paddy approximation, if you choose the numerator in this way, this should get the same result. Well, in Paddy approximation, you are also allowed to select the degrees of numerator and denominator independently. It does not have to satisfy this requirement. You can select them independently. So these are the differences of Paddy approximation. By Paddy approximation, it is introduced by a French mathematician 1 century ago, I think. And the aim of Paddy approximation is to use a rational function to approximate the original given function. And the function, the Paddy approximation can be obtained like this. Suppose the original function can be expressed like this, which is a polynomial expression of Taylor series, Maclaurin series like this. This is the original function. And by means of Paddy approximation, we can have a standard form of Paddy approximation like this when we denote G, M, R, which means numerator order and denominator order. We can select them independently. So this is standard form of Paddy approximation. And it is noticed that here there is a sum, and there is some there. And for Paddy approximation, normally we cannot reserve all the coefficients, all the terms. We must retain the first certain terms. For instance, we must return first R plus M plus 1 term. But I think we must reserve these terms and truncate the others. We cannot reserve all the terms. And I will explain this one to you, why we need this number, this term numbers. So now, if we want to have this one equals to the finite sum of this one, which we can simply denote it like this. And here there is a finite term summation, and then we can multiply both terms, and we finally get a result like this. And this part is a polynomial, this is a polynomial, and this is also a polynomial. So you multiply them together, it is still a polynomial. So the left-hand side is a polynomial, the right-hand side is a polynomial. And it should be denoted like this. And if this equation holds, then the coefficients of these polynomials should be the same. And finally, if we compare the polynomials on both sides, then we can easily establish equations. I haven't listed details of this one in the slide. So you can finally establish equations like this. And from the equations, you can establish two matrices equations. Sorry, I will not explain too much about the mathematical details of it. And you should have mathematical